Archaeological orthodoxy describes a construction process involving thousands of laborers dragging massive stones across the desert using hemp ropes and wooden sleds. This model faces a significant mechanical paradox. The laws of static friction for a 100-ton mass, combined with the physical hardness of granite, present obstacles that exceed the capabilities of soft copper tools and organic ropes. A powerful subterranean shockwave can abruptly shake a massive granite block, overcoming the resistance that keeps it inert on the sand. The resonant builder hypothesis proposes an alternative. Ancient architects utilized precise acoustic engineering to manipulate mass. Acoustics, in this technical framework, refers to the application of high-intensity wave physics to alter the structural properties of solid matter. This investigation analyzes three specific engineering challenges: overcoming static friction for transport, machining hard quartz granite, and the calibration of architectural spaces to interact with human neurobiology. These methods represent advanced applications of physical mechanics native to Earth. Analyzing ancient ruins as highly calibrated machines reveals the sophisticated logic required to move and shape these megaliths. A 100-ton block generates a massive opposing vector of static friction. This force locks the mass in place against the ground. Initiating movement through mechanical pulling requires force that exceeds the tensile strength of ancient materials. Near-field acoustic levitation provides a solution to this mechanical blockade. When an acoustic frequency matches the resonant length of a stone block, it induces elastic deformation. This causes the block to perform microscopic jumps thousands of times per second. This vibration destabilizes the contact layer beneath the stone through acoustic fluidization. High-intensity sound waves passing through the sand cause individual grains to lose contact, transforming the ground into a pressurized liquid bed. The stone surfs on this fluidized medium. The force required to initiate movement drops exponentially towards zero. Achieving directional movement requires adding mathematically related integer harmonics to a pure sine wave, creating an asymmetrical sawtooth wave. This waveform creates a fast-push, slow recovery cycle. The block kicks the fluidized sand harder in one direction than it pulls back, causing the megalith to migrate forward. By tuning these precise frequencies, ancient engineers allowed massive stones to effectively surf forward with minimal guiding force from the laborers. Shaping granite presents a second engineering challenge. Soft copper saws, rating a 3 on the Mohs scale, cannot physically cut granite, which rates between 6 and 7. Ultrasonic vibration-assisted drilling utilizes acoustic energy to overcome this hardness differential. In this model, the copper tube serves as a sacrificial carrier for energy and abrasive material. A fluid slurry of water and quartz sand is introduced into the cut. High-frequency longitudinal vibrations driven down the copper tube force the hard quartz sand grains to embed into the soft copper edge. The vibrating tool acts as an ultrasonic jackhammer, fracturing the granite at a microscopic level millions of times per second. Analysis of granite drill cores, such as those measured by Flinders Petrie, provides forensic evidence for this method. Petrie documented a feed rate of 0.100 inches per revolution. This is 500 times faster than modern industrial diamond drills. The spiral grooves cut deeper into the harder quartz crystals than the surrounding minerals. This deeper cut indicates the use of acoustic brittle fracture, which shatters the crystalline lattice of the hardest minerals first. Megalithic builders hauled massive granite blocks hundreds of miles, even when local limestone was abundant. Granite offers a high Q factor and a 25% quartz content, allowing it to sustain internal resonance. Quartz is piezoelectric. Applying mechanical stress or acoustic resonance to the stone generates a massive localized electrical charge. When exposed to high-amplitude acoustic tones, these microscopic quartz crystals begin to deform, rapidly generating localized bursts of intense electrical energy. These amplitudes can trigger resonant plasticity, or thixotropy. Intense vibration temporarily disrupts ionic crystalline bonds, making solid stone briefly malleable. Forensic evidence of this localized melting phenomenon can be directly observed at the massive unfinished obelisk in Aswan. The repeating scalloped scoop marks match the signature of a vibratory acoustic plow, slicing through temporarily plasticized stone. Ultimately, the final megalithic structures function as massive passive acoustic amplifiers for human biology. Megalithic sites worldwide share a specific resonant frequency, tightly grouped between 110 and 111 Hz. Clinical data shows that exposure to a 110 Hz standing wave induces a physiological shift in the human brain. This frequency suppresses the analytical left prefrontal cortex while activating the holistic right prefrontal cortex. The King's Chamber at Giza operates as a precisely tuned Helmholtz resonator. Inside the King's Chamber, the granite sarcophagus rings at a resonant frequency of roughly 117 Hz. The surrounding chamber responds at 121 Hz. The interaction of these offset frequencies generates a secondary beat frequency in the airspace. The resulting 4 Hz infrasound the probe matches the human brain's delta-theta border, a state associated with deep focus and healing. These structures utilize the same acoustic principles used during construction to synchronize human neurology. The tools used to inject these frequencies are documented in ancient iconography. Artifacts like the Jed pillar feature a central column topped by parallel extensions. These function as stacked plate resonators designed to amplify and tune standing waves. The symmetrical extensions facilitate impedance matching, the efficient transfer of high-frequency vibrations from a tool directly into the stone. The Wa scepter utilizes a distinct forked base, mirroring the geometry of a mechanical resonator used to direct tone. Megalithic bosses, the uncarved protrusions found on blocks globally, served as transducer terminals. Rhythmic strikes against timbers placed at these points delivered point source vibration into the stone's crystalline structure without fracturing the surface. The resonant builder hypothesis demonstrates that ancient civilizations harnessed pragmatic acoustic physics to reach these engineering heights.